Hello, this is Mr. Jackson with Chemistry, and today I'd like to talk about orbital diagrams and electron configuration. It is talking about electron placement within the cloud. So I really want you to take a moment here and just be patient as we go through it. First, I will be honest with you, it'll seem very, very weird, but it will make sense as we move along. So this is an address system for electrons within every atom. And I want you to keep in mind that everything I'm going to teach you today is actually encoded by the shape of the periodic table. And I'm going to show you how to find these things without really having to memorize very much information. Okay? So, first thing we know is that we want to talk about these two types of ways of identifying all the electrons in an atom: an orbital diagram and electron configuration. So the first thing we know is that there is a nucleus, and in the nucleus is protons and the neutrons, but outside the nucleus in the cloud is electrons that exist in specific energy levels. Now, they are not moving around in circles, but they are found at certain amounts of energy. So some electrons have low energy, some have higher energy. It can be found farther from the nucleus, and some have even more. And there are numerous numbers of levels that are available, but they're not moving around in perfect circles. They're appearing and disappearing into places because they're moving at the speed of light. Okay? So these are electrons. There are many levels within this thing, in these clouds. In fact, there's upwards that we know of as 7 levels, which are found by most periodic tables, have numbers on the left side. So up to this point, we have discovered 7 levels, but there are even more available that we don't know of right now, or atoms that don't have enough electrons to fill the other ones. And an electron must have more energy to exist at a higher level. So these have a certain amount of energy, but if you move to level 2, so there are numbers to these levels, and there are numerous levels to go out. So we'll just let you know that there are more than one. Okay? So there, each level is given a principal number like 1, 2, 3, 4, 5, 6, 7. Okay, and I showed you those a minute ago on the periodic table. Okay, and they're found on the left side of the periodic table. So some periodic tables like this one didn't have them, but a lot of the other ones I have do. So I just number them, knowing that this hydrogen atom has 1 energy level in its electrons. Calcium has to use 4 energy levels to hold all of its electrons. Okay? Then we need to move on. There's some vocabulary in the cloud. We'll talk about that. The valence shell is the highest energy level being used. So if we're talking about neon, neon is found on the 2nd energy level of the periodic table. So that means neon's highest level that it uses is the 2nd energy level. So that would be its valence shell. If you go to another element that's using the 3rd energy level, that would be the valence shell. So the valence shell is just the outermost shell being used by any element. It depends on how big it is. Okay? The kernel is all the lower levels. So if I was going to, including the nucleus, so if I was going to talk about neon, where it has electrons in the 2nd energy level, this would be its valence, but the 1st energy level and the nucleus would be considered part of its kernel or its core area. Okay? Each principal energy level can divide into sublevels. So each level can have a certain shape. We'll call it a sublevel. And these are given letter representations. So the 1st energy level could have shapes of S. The 2nd energy level has ability to split and actually form S and P type shapes of orbitals. What is an orbital? An orbital is just a region in space where atoms can be found. There are circular shapes, and a 1s orbital is smaller, closer to the nucleus, but the 2nd energy level, remember, is farther away, so it's bigger, and it's got a circular shape. Then there are also p orbitals that are kind of weird lobal shape, and there can be d orbitals, and d orbitals get really strange. They are really unique looking orbits, but they're just an area or a space within the atom where you could find an electron of that type of energy. So it's just the shape of its house, and they're kind of weird. We don't need to know those. We just need to know that there are different kinds of orbitals available. And the higher you go, the more orbitals that are available. So if you go to the second energy level, there's 2 types of orbitals available. If you go to the third energy level, there are 3 orbitals available. There's always an S, then there's always the next level is a P, and then here we go to a D type orbital. Okay, so they have letter representations. Okay, and we know as many as 4 shapes. Okay, think of it as this way. Not everybody's house has the same shape. If a person has more money or more energy, its shape of its house gets bigger and more complex. Okay, so here's what we've learned so far. We have energy levels, 1, 2, 3, 4, 5, whatever on out. These levels can split into different shapes because the electrons on those levels have more energy than other ones on the same level. So some exist in a circular shape or spherical, S. Some live in a P-type lobe shape, okay, and can hold more electrons because they have a little bit more energy than the S. Then if you go even higher, then as you get farther out from the nucleus, you can have S, P, and D. And so the number of shapes available is depending on the number of the energy levels. So 1 has 1, 2 has 2, 3 has 3, and so guess what? 4 has 4. Okay? Now, each orbital can hold, each sublevel, these are sublevels, can hold different amounts of electrons. And S can hold up to 2 electrons, one spinning in one direction and one spinning in another direction. P's can hold 6 electrons, 2 in each space. D's can hold upwards of 10 electrons, and F can hold upwards of 14. But how do I know that? Well, you don't need to know that because the periodic table has that shape. If I go into the periodic table and I look at it, there is a column over here with 2 boxes. We call that column the S area. Then we have a box area over here, not including the helium. That goes over here, but it's been moved for a scientific reason we'll discuss later. But if you look at this one, this is got 1, 2, 3, 4, 5, 6. This is the P area right here. Okay? And so we don't need to memorize it has 6. We can just look at the boxes and realize it has 6. Then if you go to the center of the periodic table, we call this the D sublevel. And if you look, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the D's can hold 10. And then at the very bottom of the periodic table is a big long box system, and that has 14 boxes. So we don't need to memorize how many they can hold because it's actually created and built into the shape of the table. So S's can hold up to 2 electrons in a single box. P's can hold 6 electrons, but divided into 3 boxes. Each can hold 2, 2, 4, 6. D's can hold up to 10 at the max. Okay, they don't have to have 10, but they can hold to 10. And F's can hold up to 14. So that's the reason why I have different amounts of line for each one, where each line represents what's called an orbital, a direction. So what do I mean by that is each orbital, okay, an S can only fit one way in space, but a P can actually be found on the x-axis, but then there's another P that can fit on the y-axis, and then another P can fit on the z-axis. So if we look at the x, y, z planes in graphing, these orbitals can exist and hold 2 electrons and not at the speed of light collide with these electrons in another orbital in another direction because they miss each other as they're flying by at the speed of light. So sometimes the orbital can be positioned in space and hold more. So every time an orbital can be changed and not interfere with another one, it can hold 2 more electrons. So P's can hold 2, 4, 6 electrons. D's have 5 different places in space. So 5 times 2 is 10. So that's the reason why our D area is 10 boxes wide. Okay? So keep following me. We'll get back to these things. Okay? So these individual boxes are called orbitals. So here's what we've learned so far. We have principal energy level numbers. So we have the principal energy level. Within the level, we have weird shapes for each energy electron's movement area. So some like to move in a area that looks like a circle. Some like to move in that has a double lobe or 4 lobes. So these are just shapes of where an electron could be found. It's in a region or an area. But then each area can be positioned different directions in space and even can come at us. So there's 3-dimensional. So these are the directions they could point. So we have those ideas, okay? And they're just places in the cloud where an electron can be found. And each one has different shapes. And these orbitals are in the shape of the periodic table. Remember, I just showed you the S is the first 2 boxes that we have. That's been there. And then the D has 10 boxes wide, the P is 6 boxes wide, and the F is 14 boxes wide, showing the number of electrons it can hold. Okay? So let's try to put this more together and move on. So here we go. Each orbital is just a direction in space. Okay? And so each one can hold 2 electrons, but we got to be careful. They have to spin in opposite directions. Okay? And the more we go higher, we create more weird spaces for electrons to exist because they have more energy. They're flying in different patterns. And so they create different areas where they live in different shapes. Okay? And so it becomes more and more. So here's a review. An electron address is just positions in the cloud. We can have principal energy levels in our address. We can have shapes of the area they move in, and the number of electrons that can be in that area. Okay, so let's do one of these. Okay, let's say I give you, and I tell you we're working with a 3D4 sublevel. That means we're going to be looking for that electron on the 3rd energy level. We're going to look for it moving in a shape of a d orbital, and there are 4 electrons in there. Okay, that's what all that information would mean. And so we're going to start writing these kind of things for all the electrons in an atom. And it might get weird at first, but let's keep practicing it and you'll understand. Okay? But we're going to use the shape of the periodic table to help us. Okay? All that information is built in there. We'll get to overlapping sublevels here in a little bit, but let's not deal with that right now. I just want to deal with the 3 simple ideas that we need to do when we're doing an electron configuration or orbital diagram. We want to remember that we always want to build from the lowest level out. That's the Aufbau principle. Okay? Then we want to make sure that if we put 2 electrons in the same place, we're going to make sure only 2 go into each orbital at a time. So when we put 2 electrons in there, we're going to keep one spinning up and one spinning down because that's a nuclear thing, and electrons to exist in the same area cannot spin in the same direction. It would cause a nuclear event. And then we have Hund's rule, which says when there are empty orbitals available, electrons will fill the empty ones first before they pair up because they don't want to pair because they both have a negative charge. They'll only pair if they have to. Okay? That's Hund's rule. So, what does this all mean? Well, let me show you. Let's do an orbital diagram. And so here we have a couple that I've done, and I want to explain how I did them. Okay, you ready? Let's do Neon's orbital diagram. Orbital diagrams have arrows, okay? And here's how we're going to do it. We're going to do one. We're going to use the periodic table. All you simply do is you find the element you're talking about and to figure out how to draw this orbital diagram. So we're going to go use neon. Neon is over here. It has 10 protons. So in the neutral state, we're just going to consider it has 10 electrons. So here we go. Neon, 10 electrons. And I want to show you where they're at. So remember, the first rule is electrons always go into the lowest energy level first, nearest the nucleus, because there's an attraction there. So they'll fill outward. So let's start with the lowest level. So we know as we work our way to box number 10 on the periodic table, we got to pass through boxes 1 and 2. Helium really belongs over here, but I told you it was moved for a reason. We're going to consider that an S box. So I got to go through 2 S boxes on the first row. So I have to go through the first row in S area. It only holds 1 orbital. and I'm going to put 2 arrows in it, one spinning up and one spinning down. They have to be paired because there's only one box available. So you can draw a box or you can draw a line that represents a box. It's up to you. I sometimes just draw lines. In fact, that's really what I do most of the time. Okay, so you don't have to draw a complete box, but I'm just showing you that an S's only hold 2 electrons. But that fills the first row. Now we run out of boxes, so we got to go down to box 3. Box 3 is in the S area. Okay, so we have to go to second energy level. We're still in an S area. It can only hold 2 electrons, and I got to go through both of them to get to neon. So we're going to give this box also 2 electrons, one spinning up, one spinning down. Then I've run out of boxes here, so I go across a table and I enter the P area. Okay, the P area, and I need to go 6 boxes in to get to neon. Well, P can hold, the second energy level P can hold 3 boxes, so 1, 2, 3, and I have 6 electrons to put in there, but I must, because of the Hund's rule and all of them, I need to put them in empty boxes first. So I fill all the empty ones up because they like to push each other away. They're all negative electrons. But now I've run out of room and I need to put 6 in here. So now I must start to repair them and put them together. So here we go. So here's 4, 5, and 6. So this would be the orbital diagram for neon. I would find electrons in a 1s, a 2s, and 2p orbitals. In fact, 3 of the orbitals in the p, and they would all be paired up. Okay? So that's how you do an orbital diagram. Let's do another one really quick. How do you do an s orbital? Really simple. What you do is you do the same thing. And let's do, I'm sorry, for sulfur. Let's do it for sulfur. Sulfur is number 16. So we're going to write sulfur, 16 electrons. We're going to start at the top or the closest to the nucleus. So we're starting at the first energy level. We got to go through both boxes. So the 1s gets filled. So as you're going to realize, you always start with a 1s and you fill it as you work your way up to higher elements. So now we've run out of the S boxes. We're going to start at the second energy level, but it starts in the S area. So 2s comes next. I don't need to memorize this because the periodic table has that shape. Then I've run out of 2s boxes, so I'm going to go across and go to the 2p area, and I need to go through all of them to get down to the sulfur. So I'm going to go 2p. P's can hold upwards of 6 electrons. So I'm going to fill that, all those 6, 1, 2, 3, 4, 5, 6, doing opposite spins in the same box. So now I've used 10 of my 16. I've run out of second energy level places, so now I got to go to the third energy level. The first area I hit is S, so the first thing in any energy level is an S. So I write 3S, and I go ahead and fill that, working my way over to sulfur. But now to get to sulfur, I go to the 3p area, and I go 4 boxes in, and I hit sulfur. So I'm going to write 3p. I got to show all the possible boxes, but I only want to put 4 in here, so I put them in empty boxes first. 1, 2, 3, 4, and then this one has to be paired up. So I can see all 16 electrons. All of them are paired, but 2 are unpaired. And that's what we're going to use in future chapters to explain chemical behavior, because electrons don't like to be unpaired. But this address system helps me draw that out. Okay? So that's an orbital diagram system using the shape of the periodic table. Okay? And if I want to teach you in less than about 30 seconds here, how do I do a electron configuration? It's really simple. I just take all these arrows and turn them into numbers. So if I wanted to do neon's electron configuration, all I would do is I would take those 10 electrons, I would keep the designations of the levels they're on and the shapes they're in, so 1s, but I don't need to show the spinning and the individual electrons. I can just tell you there's 2 there. And in the second energy level, in the S area, there are 2. But in the second energy level in the p area for neon, there are 6 electrons. So if you turn these arrows into numbers, we have what's called the electron configuration. And so it just looks like that. Okay? And so to change sulfurs, we would just do the same thing. We would just change them into numbers. And it would be 1s2, 2s2, 2p6, 3s2, and 3p4. Only 4 electrons. This method doesn't let me see the unpaired, so this method has a purpose for other reasons, and we'll have to do that. So you'll have to do the arrow method, and you'll have to do the number method, okay? So that's called the orbital diagrams and electron configurations. You should be able to do them from now on and be able to do them correctly using the periodic table to help you out and draw them in. So I just want to introduce that idea to you today. Thank you for joining me. I appreciate it.